Welcome. My name is RyanDowney, and I'm here to give an introduction to the AC analysis equipment that is built into the National Instruments MyDAC device. Hopefully by this point you have at least a little bit of experience with it. Um, if you don't, I will try to go as in-depth as I can. Alright, so let's get started. You'll notice here that I have the instrument launcher open. This is used to access all of the built-in instruments to the MyDAC device. We will start with the function generator. Should open a window that looks like this. Alright, so what the function generator does is it outputs one of the various built-in waveforms onto the analog output pins of the MyDAC device. So you see here that we have several options. There's sine wave, triangle wave, and square wave. We can adjust various parameters about these waveforms, such as the frequency here, the amplitude, notice it's in volts peak to peak, and the DC offset. We can also choose which of the two output pins it outputs on. We're just going to keep it on analog output 0 for now. Also notice the run and stop buttons. It won't output our signal onto the output pins until we hit the run button, and it'll stop as soon as we hit the stop button. I should probably also mention under the square wave that we have the option of setting the duty cycle for our waveform. So this is the ratio of how often the square wave is high versus low. So 50%, it's 50% of the time high, 50% of the time low. Alright, well that's probably enough information about the function generator for now. We'll come back to it. We're going to open the scope now. See if I can find it. Right, so it should open a window that looks like this. You'll see on the left side of your window that there is this nice grid. This is where your waveforms will display on this oscilloscope. This is a 2-channel oscilloscope, you can see. There's channel 0 and channel 1. That means you can have 2 separate waveforms displayed at the same time on this oscilloscope. The oscilloscope measures voltage over time. So you'll have this horizontal axis, which is measuring time, and you'll have this vertical axis, which measures the voltage of your waveform. So for each of our channels here, meaning each of our waveforms, we can change the scale, which is how many volts per each of these predefined divisions here. And we can change the vertical position of our waveform. So if we don't want them both normalized about the 0 here, we could move it up, basically give it an artificial offset. We can also change the amount of time per division, which is how much time is in each of these predefined divisions along the horizontal axis here. This portion of the oscilloscope is used to control the triggering mechanism. Typically you don't have to do much with this. Basically, if your waveform is jumping around too much and you want to stabilize it, you set it to an edge. You can also, if for instance you have a square wave and it lines up with this vertical axis so you can't see it very well, you can change the horizontal position so it doesn't line up with that axis anymore. We also have some additional options under this graph properties. We can change the color of our waveforms, we can change some characteristics of our cursors, which is used for taking some measurements, and we can see and change what sort of measurements we want displayed down here on the bottom. If everything I've said so far doesn't make too much sense yet, don't worry, because it'll make a lot more sense once we're actually observing something. So let's get to that. Alright, so to observe some waveforms, we're going to need to have the output of our function generator connected to the input of our oscilloscope. Alright, so I'll give you a little look of what I have here in front of me. This is the current wiring setup I have. So you can see down here this AO stands for analog output. This is the output of our function generator. This white wire is going to what I'm going to call the positive rail here, which is the positive portion of our signal. The ground portion of our signal comes out on this A ground pin here, which I'm going to use these brown wires to denote. So this second line here is the negative rail. This portion up here has an AI, that stands for analog input. This is the input to our oscilloscope. You'll notice there's a 0 minus and a 0 plus, 1 minus and a 1 plus. This is because we have two separate channels we can observe on our oscilloscope. For now, we're only going to be using the first channel, so we're going to be using the 0. So we'll connect the 0 plus to our positive rail, 0 minus to our negative rail. And there's an A ground here and here. I just connected them. Alright, so hopefully now that that's set up, we can go back to our function generator and we can generate something. So we'll start out by setting our frequency to 400 Hertz. We will set our amplitude to 2 volts peak to peak. And we will run. See that it's running now. So we'll take a look at our oscilloscope now. Notice that there's nothing here yet. That's because we're not running yet. Let's run, and we'll see that we have a waveform here. Notice it's a square wave. That's not really what I wanted, so I'm going to go ahead and change that to a sine wave. There we go. Now we have a nice sine wave. If we want to sort of zoom in on it, we can change the time division to a lower. There we go. We got a nice sine wave now. We can also sort of zoom in on it vertically if we want. We can change the vertical volts per division. So for instance, going higher, we'll make it smaller. If we want it to be bigger, we can just choose a higher number. Too big and it'll go off screen, obviously. But that's pretty nice. If we didn't like, for instance, the color that this is being displayed, we can change that too. Go to graph properties here. Let's say we want it to be pink. Let's be adventurous. So we can set that, the line, and the fill. Okay, and there we go, a nice pink line. Alright, so now we can sort of look at our function generator again. We can change some settings on that and see how it affects it. So let's go for a higher frequency, double it, see what happens. And look at that, the frequency is doubled. We could also change the amplitude. Let's double that as well. Not 400, that would be disastrous. And there we go, twice the amplitude. Alright, I had a little bit of a crash, so let's just try to catch up here. We'll do a square wave next. Let's try 20 kilohertz. I think that's the maximum you can do on this function generator. 2 volts peak to peak sounds pretty good, and let's try a 25% duty cycle just to see what it does. We'll run it now. Make sure our oscilloscope is running as well. And there we go. Let's change our time division so we can get a better look at this. And we have our square wave, or at least what's supposed to be a square wave. You can kind of see at these higher frequencies, the square wave gets a little bit distorted. It looks a lot better at the lower frequency. So let's bring it down to 2 kilohertz. And put it on a scale where we can actually see what's going on. And those look a little better. Alright, so I'm going to close out of these for now. And next I'm going to show you the next part of the lab. So for the next part of the lab, we're going to produce a series RC circuit. I'll show you a schematic here. Basically, we have our voltage source, which is going to be our function generator, which connects to a resistor, which connects to a capacitor, and back to, we're going to measure the voltages at both A and B using our oscilloscope. Before we begin, I'm going to show you what I have in front of me right now. This is the circuit I built out of the breadboard. It's a little bit similar to the circuit we had before, but I added some things to it. I tried to label point A, B, and the ground here, albeit a little bit sloppily, but hopefully you can make do. We have our resistor here, our capacitor here. The other important thing to notice is that we're going to be using the second channel of our oscilloscope now. So you see at a point B here, we have a wire, this red wire here, going to the 1 plus terminal. The 1 minus terminal just goes to ground, which is our negative rail here still. Alright, so now that that's out of the way, we're going to get this out of the way here. We're going to bring our oscilloscope back and our function generator back. We're going to try to look at what the circuit does at different frequencies, sort of a rudimentary frequency response for this circuit. Alright, so to start, we're going to use a square wave. We're going to start really low, so we're going to start at 10 hertz, 10 times a second. 50% duty cycle is fine. Let's do 2 volts peak to peak. Alright, so let's turn that on. Alright, we got that going. Let's go to our oscilloscope. Let's run. You can barely see it. It's because it's so slow. We need a really long capture time. A little too long. There we go. So there we go. Let's put the trigger to edge so it stops moving around. So, a couple problems here. It's kind of difficult to see. So what we're going to do is we're going to move the horizontal position here over a little bit so that it's not coinciding with the axes here. There we go. And let's change the color back to pink again because that looked like it stood out pretty well. Alright, there we go. You'll also notice that we only have one waveform on the graph here, so let's enable the second one. We gotta run to acquire it. And they're overlapping right now. It's actually displaying them both. So what we can do is we can change the vertical position here. I'll move this one up, so let's set that to say 2. This one to -2. And there we go. At this frequency, you'll notice there's not really much difference between the two waveforms. They have about the same volts peak to peak. You can tell by these measurements down here. And this one may be a little bit phase shifted because of the capacitor, but they're about the same. So let's take a look at a higher frequency. We'll go up by powers of 10. So we'll go to 100 hertz. There we go. Gotta run to acquire. And as we expected, we get a lot more. Let's get a better look. Well, it's starting to look a little different, isn't it? Let's get an even closer look. We can get a little closer look too. Maybe we can really see what's going on. You can actually see the charging and discharging times of the capacitor. So you can guess that as the frequency increases here, these times are going to become more and more significant. Alright, so I'm going to stop that, and we're going to see if our little hypothesis here is correct. We're going to go up to 1 kilohertz and see what happens. Ooh, look at that. So we'll zoom in a little closer here, get a better look again. So you see that our charging and discharging times are taking up the full cycle now of our square wave. So it's getting more and more distorted as time goes on, and you'll start to notice that the volt peak to peak is starting to take a hit because of it. So we're seeing that we're getting less gain as we get a higher frequency. So we're going to go up by one more factor of 10, just to see if this trend continues. I bet you it will. And let's get a better look. Yeah, so we can see our square wave is getting a little distorted too, but more importantly, our capacitor voltage is not charging in time before it discharges. And you can see that the volt peak to peak is definitely taking a hit. So what we're seeing here is that as frequency increases, the voltage across the capacitor is decreasing. This is what is known as a low-pass filter, because lower frequencies will pass through at their normal or close to normal voltage, while the higher frequencies will sort of be filtered out because the voltage will drop so low. So we'll take a look at one more thing in the circuit before we go. Let's change this to a sine wave. Let's give it a little bit of a lower frequency. Let's say 1 kilohertz for now. And let's scale it properly so we can see what's going on. Maybe a little bit more. So we'll see here that it's not as obvious that the charging and discharging time is changing. But you can see the phase shift a lot easier, and you can see the volt peak to peak start to go down a little earlier. It just sort of highlights the low pass filtering aspects of this circuit. So I just went ahead and changed it to 10 kilohertz here just to see the full reduction in voltage that we get. And we see how dramatic the drop off is. So this truly is a low pass filter, probably the simplest one you can build. Alright, so anyway, that concludes the lab. Thanks so much for watching.